Okay, so let's start our lecture today. So, yeah, I'm trying to erase word. Okay, so, yeah, so I think last time we are left with the condition that the we are trying to find the lower bound where this omega 1 and omega 2 are not in the EV form, right? They are not in the normalized form. I call it normalized form. Yeah. So okay. So what happened? So okay. Yeah. I think last time I create a constant, right? So I argue that if the limit goes to 1 or like 1/2, whatever, it goes to a constant number. So that then for large number of C, right? So you have the inequality, okay. So the question is that what happened before that C reaches the large value, right? So what happened, so the question is, so what happened, so if I think we have a lower bound for this C, right? So C is between let's call this upper bound N. What is the lower bound? So I think the lower bound is just when they equal, right? So yeah, so remember like we have this this is like omega 1, and omega 1 is equal to x1. Okay, so where x1 is any positive real number, and then we have the omega 2, which is equal to x2 plus negative x2 plus iy2. Okay, x2 y2 positive real number. So and then that okay, so then this C is okay. So now we are in the case where this C is between okay, so what I'm trying to do, so what I'm fixing, so am I fixing N1 and N2, so okay, I'm fixing N2, okay, so we fix the N2, okay, and then you get the N1 is equal to, okay, so I first I divide by x1, and then I multiply by x2, I think, right? So that they cancel out, and then times n2. Yes. So that's because, yeah. So n1 times x1, n1 times x1 is equal to x2 plus times n2. Okay. So yeah. So let's say it is m. Okay. So then what would happen if the C is between these two numbers? Yeah. So that oh shoot. maybe let me just say that as that so suppose N1 is equal to C times N2. Okay. Oh, yeah. Okay, so what happens if this C is between x2 over x1 and also f? Okay, so okay, let me think. Okay, so what we want is that yeah, I think we can like mimic a similar argument as before, right? So where your so after yeah, so after you yeah, what I'm going to do so. So what I want is that I want to have the modulus of omega 1 plus omega 2, right? Oh, sorry, N1 omega 1 plus N2 omega 2. Which is K. Yeah, so intuitively speaking, okay, so let's see the idea here. So let's say that intuitively speaking, if you have N1 equal to so N1 over like x2 over x1 times N2, so then it becomes that. So let's suppose that. For example, yeah. So imagine that you're getting longer and longer, right? So the x-axis. So when you sum them up, so even imagine the omega 1 is like becomes like longer, and then but this one is also being kept, right? So this is like y 2 times n2. Okay. So how does this work? Wait. Wait, I don't think I need that complicated argument, right? Uh, yeah, I don't think I need that complicated argument. So I think the reason is that shoot. Yeah, so I think the reason is that yeah, so I think the reason is that when the yeah, so yeah, so when this n1 is equal to this x2 over x1 times n2, right? So okay, so yeah, so mainly we want to figure out this case, okay? So I think the idea is that when we have the equality, okay, so when we have the equality, so we have that what's it called? We have what? So we have the modulus of n1 omega 1 plus n2 omega 2 is less than equal to, yeah, we have already figured out some k, right? And also this n2, yeah, so these are definitely positive. Yeah, so we sorry. We have already figured that out, okay. So now, if you keep increase n1, okay, okay, so keep increasing n1. So if you keep increasing n1, no. So if we keep increasing n1, if you keep increasing n1, so how would this related to n1 plus n2 then? So when you keep increasing n1, you are like, yeah, I forgot. I think when you have n1 times omega 1, then you are dividing the whole thing by n1, and then you are yeah, I forgot. I think I made an argument that works for the previous case, right? For the previous normalized case, but in this case, I yeah I, yeah let me try to recall what I did. So basically, I think there is some rescale argument that maybe I should apply here. So namely, the idea is that you divide both sides by like let's say n1 on both sides, and then that in this case you make the n1 to be 1. Okay. Oh yeah, I think it will work, right? Yeah, so you can always assume without loss of generality that this n1 is always 1, right? And then, wait. Which one do we assume? Do you assume n2 to be 1 or n1 to be 1? If n2 equal to 1, then n1 is yeah, I think if we show like if we show this inequality is true for any for any n1 equal to 1, right? Oh, sorry, for yeah, what I'm trying to do. So yeah, for any w1 equal to 1, okay, for any w1 equal to 1, if we show that for any w1 equal to 1, wait, doesn't make sense. If w1 is equal to 1, if I rescale it, yeah, so I think, oh yeah, so if we find a constant, okay, okay, so so it is enough to show the inequality, or to establish the inequality for w1 equal to 1 and also w2 is equal to negative what do you want to use? What letter do you want to use? A2 plus B2 plus IB2. Okay. Because if we show that if we establish for this inequality, right? So then what we do is that for this general case, what we do is because this W2 is arbitrary, right? So then for this W2, what we do is that we just let this A2 to be what do we do? Yeah, we just let the A2 to be x2 over x, okay. and yeah, yeah, suppose that we show the general case, okay, suppose that we show this special case, and then how do we move this case to that case? So since the reason is that if we have the inequality, so square root of square root of n1, so let me just say that modulus of n1 times 1 plus n2 times negative a2 plus ib2 is bigger than or equal to some constant times n1 plus n2, right? And then then let so for any, so then you let this, so there is a constant, I think, scared me. Okay, I think this constant really depends on this A1, A2, okay. I think the reason is that for different A1, A2, you will get different constant here. Okay, so then you let this A2 to be just x2 over x1, and then you let b2 to be equal to this y2 over x1. Okay. Yeah, so this is x1. So this is the general case. And then once you do that, then you multiply, you bring the a2 and then b2 in there. And then on both sides, you multiply by x1 on both sides, right? Then this constant becomes x1 times k, which is also a positive constant. And then if you multiply x1 inside, then so the left hand side will be equal to you just multiply inside by x1, and then the equality will also hold, right? So, and then when you multiply the x1 in, this becomes n1 x1, which is exactly the omega 1, and then this becomes the exactly the omega 2 that's in our general case. Okay, yeah. So so right now the question becomes what happens if this W1 is equal to 1, and then this W2 is any arbitrary, like negative A2 plus IB2, right? Okay. Okay, so what do I think of? Yeah, so what do I really think of in this case? Yeah. So what do I? Yeah. What did I show? Like, uh, yeah. So in this case, um, yeah, I think we have established the case where this uh, so the case where okay, so the case where this n1 is equal to a2 n2, right? Is because before that we have already showed the most general case for the n1 is equal to this ratio times n2, and then n1 is less than this ratio times n2. Yeah, so we have already shown that. Yeah, so and then the question becomes, yeah. I think yeah, I think there is like a inequality that's help us reduce to a case. Yeah, so what is the idea, right? What is the idea that I just used before? So this is okay, so let me try to recall. So if it is normalized case, right? You have 1, 1, 1. So then after that, because okay, so when you try to increase, okay, let's suppose that let's just try to recall what happens for the normalized case. Let me try to recall what I did the previous case. So okay, so if you try to increase, so here if n1 is bigger than n2, so namely we have something more here after adding them, right? Okay, so if you have n1 bigger than n2, yeah, so if you have n1 bigger than n2, if you have n1 bigger than n2, then what happened? So what happened with the modulus? wait. Okay, so the modulus. Okay, so the modulus. Okay, so this modulus. Oh. Wait. Oh, okay. Okay. I think I created a okay, so okay. Yeah, so I created an upper bound for this. So okay. Okay, so the upper bound is okay, I think it's like n1 n1 equal to 3n2, right? Wait, why is that? So why it is 3? So because 1, 2, 3. Okay, so okay, so okay, okay. Let's say that this n1, if this n1 is bigger than this 3n2, then yeah, people always forget about stuff. Okay, so then we have this n1 omega 1, which is just n1.